Section: Introduction. In this section, we discuss the advancements made by transformer-based large language models, LLMs, in AI research, noting their impressive performance across various fields. However, we also recognize that scaling these models can lead to unnecessary complexities, which can increase deployment costs and resource requirements. For example, deploying Llama 2 to 70B requires more than 128 GB in FP16 precision, exceeding the capacity of a single A100 GPU, but we can reduce its depth without greatly affecting performance. While previous studies have aimed to enhance LLM efficiency by eliminating redundant parameters or architectures, many of these methods apply general techniques that do not consider the specific features of transformer architectures. Transformers consist of multiple stacked blocks, each with an MLP layer and an attention layer, which serve different purposes and have varying levels of redundancy. This observation drives us to investigate the redundancies within transformers more closely, focusing on the most critical components. We systematically analyze redundancy in three main transformer components: block, MLP, and attention. By using a similarity-based metric, we assess the importance of each component and progressively remove those deemed redundant. Initially, we try a block drop method, but we find that removing entire blocks significantly harms performance, indicating the need for a more detailed approach. We then examine the separate pruning of MLP and attention layers. Our results show that while removing MLP layers negatively impacts performance, we can prune a significant number of attention layers, key to the transformer's unique structure, without degrading performance. For instance, dropping half of the attention layers in Llama 2 to 70B maintains similar performance to the full model, highlighting substantial redundancy in these layers. Building on these findings, we propose a more adaptable method called joint layer drop, which targets both MLP and attention layers. By combining the importance scores of these layers, we discover that jointly removing low-importance layers from both types yields better performance under high sparsity conditions than pruning just one type. Our work illustrates that attention layer redundancy is not only considerable but also consistent throughout different training stages, suggesting it is an inherent characteristic of transformer architectures. These insights pave the way for more efficient transformer designs, reducing memory and computational costs while preserving performance. In summary, our main contributions include an in-depth analysis of redundancy in the block, MLP, and attention components, revealing unexpected redundancy within the attention layers. We introduce attention drop, a straightforward yet effective algorithm for removing redundant attention layers without training. Additionally, we present joint layer drop, which enhances performance at high dropping ratios by targeting both attention and MLP layers. Our extensive experiments show that dropping attention layers, such as removing 50% in Llama 2 to 70B, results in only a 2.4% performance drop while achieving up to a 48.4% speedup. We also demonstrate that attention layers maintain high redundancy throughout training, indicating this is a fundamental property and offering valuable insights for future architecture design. Next, we explore related works in the field. Section Summary. In this section, we explore the redundancy within transformer architectures, particularly focusing on the block, MLP, and attention components, and propose methods like attention drop and joint layer drop to efficiently prune redundant layers. Our findings indicate that a significant portion of attention layers can be removed with minimal performance loss, leading to improved efficiency in deployment while maintaining model effectiveness. Section: Methodology. In this section, we outline our methodology for identifying and removing redundant modules in large language models, LLMs. We start by introducing a similarity-based metric to evaluate redundancy in both attention and MLP layers. From this analysis, we create two specific techniques, MLP drop and attention drop, to effectively eliminate redundant components while maintaining model performance. To evaluate redundancy, we use a similarity-based metric that measures how similar a module's input and output are. Our main idea is that redundant modules produce outputs that closely resemble their inputs, indicating they make minimal changes. In contrast, important modules significantly alter their inputs and should be kept. We quantify the similarity between the input and output of a module using cosine similarity. The importance score of a module is calculated based on this similarity, with higher similarity leading to lower importance scores, which indicates redundancy. We then identify and remove the modules with the lowest importance scores based on a set pruning ratio. Next, we consider the structure of transformer models, which consist of stacked blocks that function as subnetworks. To simplify the model, we first look at dropping entire blocks that are not important. We assess redundancy by calculating the similarity between the input and output of each block. For each block, we compute an importance score based on its input and output. By evaluating these scores from the shallowest to the deepest blocks, we can identify and remove those with the lowest scores, thus saving memory and computational resources. However, we recognize that block drop can be too aggressive, potentially removing essential layers since it does not consider the detailed architecture within each block. Each transformer block contains both an attention layer and an MLP layer, which serve different purposes. Therefore, we evaluate the redundancy of each layer separately by measuring their importance scores using various calibration datasets, from pre-training to instruction fine-tuning datasets. This analysis reveals different redundancy levels between MLP and attention layers, prompting us to develop more precise dropping techniques, namely MLP drop and attention drop. In MLP drop, we note that each MLP layer includes a layer norm operation and a residual connection, which preserves part of the input in the output. To accurately assess the importance of the MLP layer, we treat it and its layer norm as a single unit. This ensures a more precise measure of importance, allowing us to remove both unimportant MLP and layer norm layers. Similarly, for attention drop, we also consider the attention layer and its layer norm as a single unit. We calculate the importance score for the attention layer in the same way. Both MLP and attention layer drops are executed in a single step, calculating importance scores once and removing redundant layers without the need for a lengthy iterative process. We evaluate the effectiveness of this straightforward one-shot technique in the appendix. Section Summary. In this section, we present our methodology for identifying and removing redundant modules in LLMs using a similarity-based metric to evaluate the importance of attention and MLP layers. We develop two targeted techniques, MLP drop and attention drop, to efficiently prune redundant components while maintaining model performance, treating each layer and its associated layer norm as a single unit for more accurate importance assessment. Section: Implementation and loading the pruned model. In this section, we discuss how to implement and load the pruned model. After eliminating unnecessary layers, we can easily load the pruned model using existing libraries like Hugging Face transformers, with just a few minor changes to the model settings. More details on the implementation can be found in the appendix. Next, we explore the effects of removing different target modules. To measure the balance between performance loss and speed improvement, we introduce a new metric called the speedup degradation ratio, or SDR. This metric is calculated by looking at the percentage change in average performance across tasks and the percentage of speedup achieved. Essentially, this ratio tells us how much performance decreases for each 1% increase in speed. A lower value indicates that we can gain speed with minimal performance loss, while a higher value suggests a significant performance drop relative to the speedup, which is less desirable. We summarize our findings in a table and figure that show the impact of dropping various modules, such as block, MLP, and attention layers. The table presents the performance effects of removing a set number of modules, while the figure analyzes a wider range of removal ratios from 0 to 100%. When we drop block and MLP layers, we see a significant decline in performance, even though we achieve moderate speedups. For instance, removing 4 blocks results in a 2.4% average performance drop for the Llama 2 to 13B model, with a speedup of about 1.11 times. However, dropping 8 blocks leads to a 7.5% performance decline, with a modest speedup of 1.24 times. Similarly, MLP layer removal shows a small decline at 4 layers but a larger drop at 8 layers, indicating that while we gain some speed, it comes at a considerable cost to performance. In contrast, when we drop attention layers, we find minimal impact on performance, which is quite surprising given their importance in transformer models. Both Llama 2-13B and Mistral 7B maintain over 99% of their original performance even after removing 8 attention layers. For example, after dropping 8 layers, the performance remains nearly the same, with a speedup of 1.23 times and a low degradation ratio. Even dropping 12 attention layers results in only a slight performance decline, showcasing that attention layers are quite redundant and their removal is an effective pruning strategy. To confirm our results with larger models, we examine Llama 2-70B, which also belongs to the Llama family. We find that dropping a small percentage of blocks or MLP layers leads to significant performance drops, while attention layer removal continues to perform well. For instance, dropping 40 out of 80 attention layers results in a speedup of 1.48 and a low degradation ratio. This consistency across model sizes indicates that attention layers can be removed without greatly affecting performance. Overall, our findings suggest that attention drop is the most efficient pruning method, allowing for substantial speed improvements with minimal performance loss. In the following sections, we will delve deeper into the efficiency gains from attention drop and further analyze the importance of attention layers in the model architecture. For more comparisons with other compression techniques, we refer to the appendix. Section Summary. In this section, we investigate the effects of dropping different target modules in pruned models, introducing the speedup degradation ratio, SDR, to quantify the trade-off between performance loss and speedup. Our findings reveal that while dropping block and MLP layers leads to significant performance degradation with moderate speedup, removing attention layers maintains high performance with minimal impact, making attention drop the most efficient pruning strategy across various model sizes. Section: Efficiency of attention drop. In this section, we evaluate the efficiency of attention drop regarding memory usage and inference speed. We look at how much memory is saved by using the key value, KV, cache and measure the speed improvements during the entire generation phase. Our results show that attention drop significantly enhances both efficiency metrics while still performing well. For KV cache memory reduction, we note that since attention generates outputs one token at a time, the KV cache stores intermediate representations of input sequences. This cache speeds up inference by avoiding repeated calculations, but it can consume a lot of memory, especially with longer sequences or larger batches. Our attention drop method effectively removes less important attention layers, leading to a smaller KV cache. We compare the memory usage of the KV cache before and after applying attention drop across various models, using multiple NVIDIA RTX A6000 Ada GPUs. The results indicate that attention drop leads to considerable memory savings for all models tested. For example, in Llama 2-13B, the KV cache drops from 52 GB to 26 GB, a 50% reduction. In larger models like Llama 2-70B, the KV cache decreases from 20 GB to 10 GB. These results are based on scenarios with limited resources, and in cases with more resources, the memory savings from attention drop become even more significant, benefiting both memory-constrained and memory-sufficient environments. Next, we assess the speed improvements from attention drop. We measure inference speed throughout the entire generation process, from the input prompt to the final token. To ensure accurate results, we follow two principles. 1. We perform all operations on a single NVIDIA RTX A6000 Ada GPU to avoid communication delays from using multiple GPUs, and 2. We increase batch sizes to optimize GPU usage for each model. For Llama 2-70B, we use 4-bit quantization due to its size, while for Llama 2-13B and Mistral 7B, we use 16-bit precision. We input a sequence of 2048 tokens and generate an additional 2048 tokens, capturing the full inference process. The speed-up ratios from attention drop are presented in our tables, showing up to a 40% increase in speed while maintaining over 95% of the original model's performance. Additionally, we find that the efficiency of attention drop is better than that of MLP drop and block drop, especially at higher speed-up ratios, indicating a more effective balance between speed and performance. We also visualize the importance scores and the order in which layers are dropped in pre-trained models. By examining historical checkpoints, we explore how these importance scores change during training. We observe that deeper layers, except for the last ones, often show low importance across block, MLP, and attention modules. Our analysis of dropped modules reveals that both Llama 2 to 13b and Mistral 7b tend to drop deeper layers first, followed by shallower ones, consistent with findings that deeper layers are more redundant. Larger models like Llama 2 to 70b show a similar trend. Finally, we investigate the consistent redundancy of attention layers throughout training. By revisiting historical checkpoints from MAPNEO7b, we track how layer-wise importance scores evolve. Our findings indicate that attention layers consistently have lower importance scores than MLP and block layers at all training stages. While the importance of MLP layers and blocks increases over time, attention layers change more slowly, suggesting that their redundancy is a fundamental characteristic of attention layers.